and I will be talking about some interesting problems on mechanical instabilities and transport phenomena in two-dimensional systems. So a quick outline, I will talk about my motivation, what got me interested into these kind of problems, together with grand challenges in the field, and that makes up about the first half of the 20 minutes. And in the remaining time, I will show some representative research work done at IIT Madras related to the mechanics of membranes and how transport, electrical and thermal transport happens through the system. Quick introduction is this small honeycomb is my research area, and this is me, and it would not be interesting enough if I just talk about this. Unless I talk about the broader research area, I would not be able to convey the excitement in the field. There is one more motivation why I made this sketch as an introduction, and that has to do with this honeycomb lattice. This honeycomb lattice is the lattice, the crystal structure which graphene has, and that is one of the primary materials whose properties I would be discussing today. I'll start with the following, that graphene is a two-dimensional electron gas, and if you make a Hall bar with it and cool down to low temperatures, say 4 Kelvin, and apply a very large magnetic field perpendicular to it. How large could be 10 Tesla, 14 Tesla. For people who are not into this, I'll just remind that a Tesla is many orders in magnitude larger than the Earth's magnetic field. In fact, 10 Tesla is like 7 orders larger than the Earth's magnetic field. If you apply that large magnetic field, then you get these oscillations in the longitudinal resistivity, which are shown here. And you also get very precise plateaus in the Hall conductance. And in fact, this has become the definition of 1 ohm, the amount of Hall conductance you have, because that is defined in terms of the units of E square by H. So this is all very well known, and I'll just tell you a short story how I got interested in this field. About 10 years back, when I was doing my postdoc at NUS Singapore, we were doing one of these routine experiments. In the routine experiment involves, you take one of the graphene samples and sweep your gate voltage. So in this transistor, when you sweep the gate voltage, you look at the band structure, the Fermi level goes into the conduction band or goes to the valence band. And as a result, the resistance increases when it is close to the Dirac point here, and then decreases on both sides because both holes and electrons can conduct. So this is a typical resistance versus voltage curve you measure at room temperature. And we cool down, measure the resistance versus voltage at low temperature, and then apply a magnetic field and measure what kind of quantum Hall effect is present in the system. In this particular late night experiment I was doing, I measured this curve at room temperature, then I cooled down, and I realized that there are some oscillations coming, very periodic oscillations coming in the plot. And that struck me, maybe I forgot to take the zero field data. So what I should do is switch off the magnetic field, first record the zero field data, and then switch on the magnetic field. I got up to do that, and to my shock, the magnet was already switched off. There was no magnetic field applied. And remember this, there is no small leakage which can be responsible for this. This behaved as if a giant magnetic field was passing through the sample. The positions of these oscillations were exactly where you would expect them if a large several Tesla magnetic field was passing. And this phenomena had a connection with some theoretical predictions and a related experiment. I made a record of this in my lab book, Zero Field Quantum Hall Effect from Pseudomagnetic Field. And we could not publish it because it was not a reproducible thing. We got it by accident. But this is probably the only known record I know of a transport experiment showing zero field quantum Hall effect. How does this effect arise? People have seen the same using measurement of density of states, using scanning tunneling spectroscopy in accidentally grown bubbles. So if you take CVD graphene on platinum, then you get these very sharp bubbles that you can see in this picture here. And experiment has revealed that the magnetic field, not the real magnetic field, a pseudo magnetic field as giant as 600 Tesla can be present at these sites, and which is also confirmed by theory, because this samples are highly strained. The membrane is highly strained at this location, and that a strained field translates to an effective gauge field in the Hamiltonian, and that is responsible for this very unique phenomena. While these things have been shown and they are exotic quantum phenomena, but people still lack any means of controlling the membrane mechanics. If you ask me, can you create this again? It's impossible. You can't dictate how the membrane should have a particular shape. It's a grand challenge in the field to develop control on the membrane mechanics in order to realize these very novel phenomena. This has given birth to ideas such as origami and kirigami electronics. Origami, as you know, is the art of folding paper to create all these beautiful structures that you see. And if we could do the same with membranes, atom thin membranes, then we could realize entire circuits which have not only high mobility transistors, electrodes, but also built-in pseudo-magnetic fields which can't be achieved with a superconducting magnet. Yet we are nowhere close to doing this in a reproducible manner. One or the other experiment here or there has shown this. Another motivation, the second motivation which I will share of the larger research field is related to the following. The red blood cells which flow in our body, they have very large size, typically like 8 micrometer. And they are required to pass through capillaries which are only few micrometer, 3 micrometer or 4 micrometer in size. And how they do that is captured in this image, which is using a microfluidic channel. You can see this red blood cell has to change shape in order to do that. And this is actually very surprising because the membrane is not just a fluidic membrane. In fact, there is a cytoskeleton, which is a tethered membrane. And in a tethered membrane, you have a triangular lattice as shown here. You have nodes and you have connecting worm-like polymers. So this has to maintain the structure under different conditions. And what makes this problem special is that the cell is incompressible and the surface of the cytoskeleton is non-dilating. So someone compared this problem with the following, that you take a sheet of paper and you are asked to take this sheet and fold it up without cutting into a spherical shell. That's impossible, as everyone knows. And this is also similarly quite impossible, but it works. It's much more complex. What happened is that these ideas led to an explosion of theoretical work in this direction. They were inspired by the biomechanics of red blood cells, but you cannot test everything with red blood cells. So people thought, what are the other kind of membranes which will do the job? And that is where graphene related membranes came in picture, because this is a canonical membrane, a tethered crystalline membrane, where instead of the worm-like polymers, you have covalent bonds and a very neat honeycomb structure. What you have, one of the predictions I'll just mention, you have competition between deformation energy and entropy. And there are theoretical predictions that graphene should undergo a crumpling transition. And why these are grand challenges, the crumpling temperature predicted is 70,000 Kelvin. So no experimentalist is going to touch this, but then there are workarounds and some people are still trying. So this is one of the grand challenge in the broad field. Now I come to some of the related research I did in this area. And one question we looked at is, what are the configurations that a two-dimensional membrane takes on a corrugated substrate? So imagine you have put a graphene or any other two-dimensional membrane on a corrugated substrate. We may ask, will it follow the substrate as in the image on the right, or will it not follow the substrate as in the image on the left? And this depends on the energy cost of bending and stretching of the membrane, as well as the energy cost of adhesion. And so there is a competition between deformation energy and adhesion instead of deformation energy and entropy. Theoreticians like to write an equation such as this one, which describes the in-plane deformation, the bending energy, and a contact potential describing the adhesion. To look at this problem, we developed a 4-dimensional lithography where imagine we put polymer resist, but this is not a usual resist. We can code this resist to swell in the Z direction, out of plane direction, and that swelling can cause the aspect ratio to increase substantially. So we begin with a resist which is small, and we could make it to increase by 10 times in height. And then we ask the question whether this graphene will follow the resist or will it not follow the resist. You can see here when we expose this resist to a certain chemical, its height changes by a factor of 10, nearly factor of 10. So we have a strong control and a precisely controllable value of the aspect ratio. So what we did is we put these 2-dimensional membranes on top of these pillars and studied how they get strained or they get delaminated. And there is a very beautiful theoretical prediction in this direction. People have considered this membrane attachment and detachment problem as a phase transition. And one can, for example, look at this phase diagram where height fluctuations versus the lateral length scale, which are characterizing the parameters, the geometrical parameters, and your membrane can be in an attached state or a detached state, depending on how much fluctuations you have over a certain length scale. So with these tunable lithography patterns, we could take the system from an attached to a detached configuration. And not only that, we could estimate the strength of the adhesive energy, which is the value we found 2 milli-electron-volt per angstrom square. This is one way, but there are many other ways in which mechanical instabilities can be brought in. The previous one is known as the snap-through instability. Here, if you take a sheet of polythene or any other thin film, you can stretch it in one direction, and that creates a quasi-periodic wrinkle array. And these are very difficult to solve in theory. They involve very difficult nonlinear partial differential equations. But there are very nice scaling laws developed by Sarda and Mahadevan. And from these scaling laws, we can understand what would be the wrinkle wavelength and wrinkle amplitude under a given condition of stretching. So for example, here there is a stretched polythene sheet, a very common object, and we have measured the wavelength as a function of some power of the strain, and it follows the universal scaling law. This kind of a stretching can also be experienced when systems undergo thermal expansion mismatch. For example, you put single layer CVD graphene on copper where it is grown and cooled down. You can generate, if you grow them on molten copper, you can generate extremely aligned wrinkles. And we looked at how this wrinkle morphology is important in the correct determination of the thermal expansion coefficient of this system. What does this universal scaling law say? It says that wrinkle patterns, whether you start from curtains or apple skins or human skin or polymer, they're all the same. The same law holds all the way down to graphene. But we did one interesting experiment. You take a multi-layer graphene oxide sample, and if you stretch it in one direction, you get these wrinkle patterns, which are wrinkles are oriented following the universal scaling law. They are oriented along the strain direction. They keep reducing the width, and there comes a transition when the width is comparable to the wavelength of these wrinkles. So this is the width of the interconnect we made, about 10 micron or 5 micron. And then we see that the wrinkles get completely oriented in a different direction. And this very surprising result, where the universal scaling law does not seem to hold, has important implications. What it tells us is that if you make devices out of it, which are from bulk samples or 80 micron thick, wide graphene, then you can get a reversible response if you change the resistance as a function of strain. But on the other hand, as you decrease the width of these interconnects, then the graphene cracks which form, they form along the entire length of the wrinkle, and therefore they tend to fold once it cracks, and the process becomes irreversible. So what we have shown is the wrinkle patterns determine the performance limits of graphene micro interconnects. Very important example where mechanical instabilities play an important role with reference to electrical transport. The last thing I will show is thermal transport. And unfortunately, we don't have any phonon meters. You can measure the electron transport easily by having an electrometer. Phonon transport has to be interpreted, and this experiment typically involves micro Raman spectroscopy. You use Raman both for heating a sample as well as we measure the shift in the Raman modes. The shift in the Raman modes tells us the temperature. So the Raman is both the source, the heater, as well as the detector of the temperature. And by solving the heat diffusion equation, we can find the thermal conductivity of the system. For example, here we have graphene on a circular hole, and this is single layer graphene, which has extremely high thermal conductivity, 1200 watts per meter Kelvin. And this is measured using the Raman optothermal technique. If your film is sitting on a substrate, the things are a little more complex because part of the heat goes through the substrate and part goes through the film. And so one has to perform more detailed experiments as well as simulations in order to arrive at the precise value of the thermal conductivity and the total interface conductance. One kind of sample that we looked at was graphene with rotational stacking faults and Moire patterns. So to illustrate what that means, a typical graphite sample will have the graphene layer stacked as AA layers or AB layers. That is one carbon atom right on top of the other, or one on top of the other, but shifted in a particular way, that is AB stacked. Now imagine if we rotate these layers in arbitrary manner, then you will get different angles and you will get Moire patterns at certain angles.
Yes, each 1 hour by a flash.
So what these samples have the tendency that they can support randomly oriented uniaxial wrinkles. And the reason is that you are having a system where there are crystallites with different orientations. And so the bending rigidity of this sample comes down and system can support wrinkles, but the kind of wrinkles which happen here are very different. They are not quasi-periodic like we saw before. They are randomly oriented. And this is one such wrinkle. So we looked at thermal transport in these systems which have wrinkles and rotational stacking faults. And what we found is rotational stacking faults suppress the thermal conductivity due to scattering from additional phonon branches which form, and also due to zone folding. But once there are wrinkles, they tend to uncouple because they cause a spatial suspension of the film. So they uncouple the crystallites and actually cause an increase in the thermal conductivity. So in many different ways, I have shown that the membrane mechanics, the formation of wrinkles, mechanical instabilities is very crucial to towards the transport phenomena, electrical transport or thermal transport. And by itself, the mechanics of membranes is a very interesting topic. I'll just conclude by thanking my current students and former students and postdocs, also our collaborators and funding agency. And thank you for your attention and look forward to questions.